Hello all, welcome to my channel. I'm back with another video. In this video, we will be seeing how Spark works with Gluten and how Gluten leverages some uh, good, nice technologies to achieve acceleration for Spark. So let's get started. So first thing first, what is in the picture you see I have mentioned Substrate and Velox and Arrow and Gluten. So Gluten is an accelerator, or it's you can think of Gluten as an glue, which combines Spark and Velox, and it does it via the use of a substrate. So substrate is a technology which allows us to read a plan, uh, 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 or we can think substrate of as an open specification for serializing any plan, and generally it is for use for SQL, but it can be used for any plan. So that plan, once it is explained or expressed in terms of a substrate, it can be read by all those systems which understand substrate, or they have an adapter for substrate. So what happens is that it will define a cross language engine agnostic format based on protobuf that describes what computation should be performed on unstructured data. Okay, so and this allows for a single query plan to be produced by one system. Let's say, for example, in this case, Spark. So Spark produces a physical plan, and then we are executing it on a different query engine. So the engine which did not generate that plan. So in this case, Velox, or let's say there are others as well. So in case of Spark with Gluten, what does this substrate does it will read the physical plan of Spark, and then it will change it, or it will apply certain relational algebra and create a plan which is understood or can be executed by Velox as well. And that's how it hands it over from a JVM system, it hands it over to the native system. This enables interoperability, like bit across heterogeneous data processing engines without we have to tie to a specific implementation or a dialect. So in this case, what can happen is Spark generates the plan. We can run it on data fusion, we can run it on DuckDB, we can run it on Apache Arrow or some other systems which implement that, for example, Velox. Then this is one part. Then we have Arrow also in picture. So Arrow is an in-memory layout or columnar data layout for efficient transfer of data between systems, which allows, again, it also allows us for interoperability. What is that is, so basically, for example, let's say if we let's take an example of Spark itself. So we are writing, Spark is written in Scala, and let's say PySpark when we are writing. So the data from the Spark in JVM environment has to come to the Python environment. And while doing that, we have to do a lot of deserialization, serialization. If we are using Arrow, which, let's say, if Java or Scala system also understands Arrow and it generates the layout or the memory format it uses is Arrow. So, and Python also understands that. Then we don't have to serialize and deserialize. That's where the benefit is coming. So that one language writes something, one one system writes represents data in a format which is understood by other systems as well. So we don't have to do serialize and deserialize. And also we can directly do a zero copy transfer of or zero copy data processing. We don't have to copy the whole content to a different context. So that's where Apache Arrow comes into picture. So if you think, so Apache Arrow, what it does, it's a universal standard for representing a tabular data, which in case can be data frame, while Substrate is a universal standard for representing the relational operations itself. And that's when we have these two combined together. So Substrate makes the API independent of the computation definition. It makes the engine independent of compilers. It makes the engine independent of computational storage. While Arrow gives us high performance for independent in-memory format, and also it in-engine optimized wire-friendly representation. So the things becomes faster. So how does that happen in case of let's say when we combine these things? So what happens is we will have an analytics DSLs, like for example SQL, Python, Scala, or we can think of it as a client interface. Then we use Arrow and Substrate to create a plan, and that hand it over plan along with some data, and that data is handed over to the query engine, which understands substrate and which understands the in-memory layout of arrow as well. So now we will have faster data transfer, faster there is no CLS and DCLS, and these engines understand this. So now we can write a SQL, Spark SQL, but gets executed on a ClickHouse engine, or we can write a Python data frame API call, and that gets executed on Velox. Now we can choose the engine that we want, because we have a substrate in between, which makes these engines also understand the plan generated by Spark. Once it is there, once it is handed over to the S3 location, these engines talk to these storage engines using Arrow, so that they don't have to do too much of data serialization and deserialization. Also, there is substrate plan in here as well for some systems. For example, if we have any storage layer on top of it, or a storage engine on top of these storage layers, if they understand the substrate plan, we can use that as well to do some kind of optimizations. For example, push down, predicate push down, or projection pruning. Those kind of things can also be understood by these storage engines. So for example, let's say mini IO, or let's say any S3 compatible system which has this subset implemented, it doesn't have to know what is the backend, whether it is mini IO, whether it is SDFS, or let's say some other safe, some other system. That also can be decoupled. So how the flow works is, the client writes a SQL query, tool running on the client side converts this SQL into a subset plan. The engine receives the plan and splits into two plans. Like in this case, push down plan and execution plan. The push down plan is sent to the storage engine. It does that, it executes that system and then sends back the results. The engine executes the execution plan which is there, and then on the filter data which is on in memory, and the engine sends that arrow data to the client. So if we see in these terms, for example here, SQL query, in this case Spark SQL query, is it generates a substrate plan using Gluten. That plan is sent to the Velox engine. Velox engine reads that, and like that this subset plan is split into two parts. One is the actual plan, the other one is the plan which needs to be pushed down to the storage engine. This is just for an educational purpose. This doesn't happen actually. We can ignore this, but let's say the plan is there, then that plan says that, okay, read some files from here on the storage side. So it reads in an arrow format, and that same arrow format is understood by this engine as well. So we don't have to, we can do a zero copy processing of the same data. And this subset plan, which is execution plan on this filter data that has to be applied, is applied. And then again, because this also engine also understands arrow, we don't have to do deserialization serialization, and simply can zero copy transfer of the arrow data as well. So this makes the whole system very fast. Now, example here, another example can be PyArrow or IBIS, which is a Python-based project for SQL dialect. So IBIS generates a substrate, which is, we can directly write SQL, or we generate a substrate plan, and the flight SQL or ADBC or any IBIS backend understands that substrate, and it chooses which engine to run on. It can be SRO, DuckDB, Velox, Data Fusion, and then storage format, Parquet, or other file format. So this makes a composable data stack kind of a solution. That's where this substrate and arrow is gaining momentum. So this is one simple example where we simply say that, okay, basically what we are doing here is, if we see, we parse certain things, and then we say, okay, whatever is the query that we have, uh, let's say the user provided some query, so it will look at those things, query, it will say that IV expression evaluation and pass that particular query that has been given. Then it will do a compiler, substrate compiler. It will generate the compiler plan. It will run with PyArrow substrate and run the query. So this is, here we are using PyArrow to run this engine, but again, same thing is, we can choose any engine that we want. This is a basic example of how we can do this with a simple uh, Python project where we have IBs as an expression builder. And how Gluten, again, Spark plan is generated, plan validation happens, then it does some transformations. Substrate plan generation is done by Gluten. Substrate is sent to the native plan, and then the expression type conversion happens. The native operator is picked up, and the native execution happens in the Spark, sorry, Velox side. So this is how Spark and Gluten use substrate and arrow to do the native execution. The flow is, Spark reads the sources, Spark data into column batches, offloaded parts Gluten passes the data to Velox natively, often already in the Aero compatible format. Velox processes the data using Apache Aero compatible vectors. Operations like filter, join, segregation are vectorized on columnar data. No row by row processing happens because Velox can very much supports single instruction multiple data and cache friendly columnar layout. Then it will results return to Spark. Velox produces output in arrow compatible format, which Spark understands. Gluten wraps converts them into a columnar batch directly to arrow buffers, passed back to JNI, which is Spark's JVM, and then Spark consumes that natively via its columnar processing, whole stage generation, zero copy, fallback to row format if the unsupported operators are there. What are the additional benefits of using this? Because columnar shuffle, we can, I mean, it does, Gluten implements a columnar shuffle. It also does a unified memory management using off-heap memory, and interoperability. It allows that, okay, we can choose the engine that we want to run that project. This aerocentric design is key to Gluten plus Velox's 10x speed up. This is columnar data plus vectorized zero copy, avoids JVM row overs and serialization costs. For deeper details, see, we can look at the repo as well. And this is the flow for, let's say, this is the flow for uh, uh, substrate. So for example, JVM will create the plan. The plan JVM Gluten will read that on the JVM side. It will see the plan, then it will create a native plan, pass that arrow data. It will then vectorize a substrate will be created. It will send it to the Velox native C++ engine. It will do the execution, return the arrow batches, arrows to column conversion will happen, and then it will feed the results back to the Spark JNN. Similarly, if we have data as well also involved in this, then this arrow comes into picture. And if we see this is stack part, if we see the growth as well, like Parquet made the whole system, like we have two different catalogs running, like not catalog, two different open table formats are running on this Parquet format, like Iceberg and Delta Lake. We have two different uh, catalogs like Polaris and Unity. Same way, something similar is happening in this composable data stack. We have Arrow as an in-memory format, which is an on top of sits on top of this Parquet file. Then we have different engines which can execute the code, and then we have Substrate, which makes like, for example, if we can use Unity to access Iceberg and Delta, then come to Parquet. Here also, if the engine understand the Substrate, wherever that plan was generated, Velox or Data Fusion can execute that and then can access the in-memory data layout. So this is how Spark works with Gluten and uh, Substrate plus Arrow to speed up the job, or a pipeline of Spark. So this was it. Keep digging deeper into this tech and keep rocking. Thanks.